Gentlemen, welcome back. I had a really cool show and tell that I wanted to do, but I already did the job and I already had to send the thing back, so I have nothing to show you. I'm going to put it up on screen. Regardless, you read the title of the video. It's one of those super niche things, even among the already small niche of electrical testing. Unless you've ever wondered, like, hey, how do I test high accuracy energy revenue meters? There's a good chance you've never heard of one, or never seen one, or never had to use one in the field. Be warned, we're going to go pretty far in the weeds on this one. It's a max level nerd. You need to know the math. I'm not going to walk you through that all the way. I expect that you know the power equation. I expect that you know a couple things. But if you're a relay tech and you've just never tested an energy revenue meter before, this is the video for you. We're going to walk through not only what the equipment is and why we need it, also how to use it, how to hook it up, and how to do the tests that we're supposed to do. Let's talk about accuracy for a second. What do we actually mean by accuracy when we're talking about a meter? How precise is the measurement that we're taking? When you look at the display for voltage or current or whatever, how accurate is that? How true is that to real life? You might think plus or minus 1% accuracy is just fine for most things. And honestly, that's not too far off. If we're measuring a 480 volt transformer, whether my meter says 476 or 484, I know that it's hot. I know that it's going to do what it needs to do. So for my Fluke 87, that's a totally acceptable accuracy. Most digital multimeters are going to be roughly that accurate. They're going to be plus or minus 1%. And they're going to be roughly that accurate across a huge range of different measurements. That doesn't really cut it when we're talking about buying hundreds of thousands of dollars worth of energy for a factory, or we're a wind farm selling millions of dollars of energy back to the grid. We need to know that we're taking very, very precise voltage, current, power, and energy data when it comes to revenue. If a 1% measurement error could cost you tens of thousands of dollars every year. And of course, we never want to assume anything that is plugged in is just going to work indefinitely. So the acceptance and maintenance testing of really high accuracy revenue meters is critical to business. And fortunately, it's a lot easier to test than it would probably seem, despite how insanely accurate the stuff needs to be. A couple things to note before we get started. Everything we work on in this industry is going to have a published accuracy. So we open up the book, see what the accuracy is listed, and that's what we test it to. Obviously, we have the technology nowadays to make almost every meter infinitely precise. I measure damn near anything to however many zeros you want. In reality, that would be insanely expensive and a huge waste of time and money, considering 99% of the work I do with my old Fluke 87 is checking to see if the new guy unplugged my extension cord. For my Doble relay test set, on the other hand, I'm going to expect a lot more from it to do more precise work. I need more accuracy. When we test and calibrate equipment in the field, the test equipment I use to test the equipment needs to be more accurate than the tolerance I'm testing it to. This feels like it should go without saying, but the reason that we use the timer built into our high current test set when we're testing breakers is because that has millisecond accuracy. Whereas if I was using a stopwatch, that would be maybe half a second accuracy, and that is not at all useful when the timing needs to be within a couple cycles. So again, something to keep in mind, our test equipment has to be more accurate than what we're trying to commission or maintain. Revenue meters come in a bunch of different classes. A common example I'm going to show on screen or show you B-roll is the SEL-735. The SEL-735 is actually what I tested yesterday with my Watthour standard. I'll put the published accuracy for that up on screen. When I test the voltage and current inputs, they need to be at least as accurate as is listed in the manual. It should be more accurate than is listed in the manual. For the energy meter portion, the class 0.1 means that it will have no more than 0.1% error for the energy it records. Now, that's at full scale with perfect power factor, but still, that's pretty remarkable considering we have stacking errors from our voltage measurement multiplied by the stacking error of our current measurement, complicated by any error in our phase angle measurement. So it's even more remarkable when we see on meters that it's got the 0.1S class accuracy. The S means that it's 0.1% accurate all the way down to 5% load and at varying power factor. Now, I'm greatly simplifying there. You can actually go, you can read the IEEE specs and see all of the things that make an 0.1S class meter 0.1S. There's kind of a lot to it, but for the sake of discussion today, we just need to know that it's really, really accurate. It's going to be 0.1% accurate at a huge range of values. So how do we go about testing a 0.1S class revenue meter? For me, as a NETA technician working for a NETA accredited company, the general recommendation for testing almost anything is that we start with the Bible, the NETA ATS or the NETA MTS. What does the book say for testing microprocessor-based meters? It says, and I quote, apply voltage or current as appropriate to each analog input and verify correct measurement and indication. And then a couple other BS things we're going to skip, doesn't really matter. Okay. Then our required test values. So the results that we need to get are, and I quote, measurement and indication of applied values of voltage and current shall be within the manufacturer's published tolerances for accuracy. Why do they say that? Sounds like a cop-out. It totally is a cop-out. It's it's sort of a catch-all, right? Because we've got different classes of meters, we've got different accuracies, we've got different ways that we can measure that accuracy for different manufacturers. So when NETA says it needs to be as accurate as the manufacturer's published data for it, we have to go to the relay manual, we have to go to the meter manual and do what it tells us. But it is interesting that it only has 2 tests. I need to test voltage accuracy and current accuracy, and that's it. I hook up my relay test set and I hit go, right? And I record what the meter says. That's all NETA requires me to do. One problem here is that the published accuracy for my Doble F6150 is lower than that of the SEL-735. Here comes the Watthour standard, or the Radian RD-21. In simple terms, a Radian RD-21 or a Watthour standard similar to that is going to be like a regular revenue meter, except crank up to 11. The accuracy is off the charts, 0.002 or 0.001% accuracy, and we can use that accuracy as a comparison point for the meter that we're trying to test. In this case, it's an SEL-735. The methodology that I have for these 2 tests is pretty simple. We're going to wire the Radian RD-21 in parallel with the meter's voltage inputs and in series with the current inputs. I'm going to put a drawing up on screen so you know what I'm actually talking about here. 2 important notes. Pushing either voltage or current into a revenue meter while it's turned on is fine, right? Because if I've got voltage and no current, I've got no power, I've got no load, it doesn't clock energy. If I've got no voltage and I've got current, that's also fine. It doesn't clock energy, it doesn't clock power. Totally fine. If I do both, I'll need the meter to be in test mode, or we're going to run up the energy counter on that. And we generally don't want to do that because it screws up the energy for our customers. A second note, the Radian RD-21 is a single-phase only test set. They do make 3-phase test sets, and I'm sure they work great. I've never seen one. I've never used one. But the Radian RD-21, single-phase, so we're going to have to do 1 phase of voltage, 1 phase of current, and then we're going to roll through the phases. We're going to do A phase, then B phase, and C phase, and do this all separately. All right, so once we're wired up, I proceed by using the control panel in Protection Suite to run my Doble 6150. You can do this with basically any relay test set, any voltage and current source where you can modulate the voltage and current magnitude and the phase angle together. So basically any relay test set is going to work fine. We're essentially just using it as a power supply here. In my case, the nominal PT secondary voltage was 110.66 volts, and the nominal CT secondary was 5 amps, pretty typical. I'm going to enable those outputs, and then I'm going to either ramp up or down in the smallest possible increments that my test set will allow, until the display on the Radian shows exactly that value that I'm expecting. So for the voltage, I want the Radian to display 110.66 volts. I don't necessarily care what my test set displays, because again, we're just sort of ignoring that. We're using it as a power supply. The Radian is my known good standard. So when the Radian reads 110.66 volts or 5 amps, I'll check the live metering data from the 735 and record my primary voltage and current readings. When I record the reading data, I make sure to note that the expected values from the standard are in secondary, 110 volts, 5 amps. And the data that I'm recording off of the The SEL, the 735, is going to be in primary. So that's going to be 3,000 amps and 230 kV or whatever. All right, so we're done. We did those 2 tests. We passed everything per NETA acceptance testing or NETA maintenance testing standard. Sticker it, pack up, and go home, right? Well, hang on. In real life, experience has taught me with, of course, real life customers, there's a little more to it than that. Generally, if you're testing a revenue meter for a customer, they want some sort of energy value tested with it. I'm not the world's foremost authority on watt-hour meter testing, so don't get me confused, but I know that you need to be able to make a solid argument to defend your results and defend your methodology when you're making a claim that something is calibrated correctly and is working. We're all here to learn, so if you've got the way that you do it and you think it's better than the way that I do it, go down and tell me in the comments. That's fine. I'd just be professional or I'm going to block you forever and curse your family. At this point, I already have my watt-hour standard and my relay test set all hooked up. There's a very quick and easy process to prove a whole lot more is working about the meter than just voltage and current. It also makes my reports look nice and fancy and long and detailed, which makes engineers scared to question me, which is the whole point of a good test report. All right, CGI whiteboard, help me out here. Energy in watt-hours equals power in watts times time in hours. Go figure. Breathtaking shit here. From that, we also need to know how we get our power. So power in watts equals volts times amps times power factor in percent. And just a quick reminder, power factor, the percent power factor, equals the cosine theta, which is the cosine of the phase angle between your voltage and current measurements. So knowing all of that, it looks like if I can record a few watt hours of energy and compare that to a known good source, that's more than accurate enough to tell that all of my other measurements, my phase angle, my time, my voltage, my current, are accurate enough to make good energy calculations. Lo and behold, our Radian RD-21 watt-hour standard is very accurate. It's a very known good source, and it has some built-in conveniences to make the process almost idiot-proof. Now, I don't mean idiot-proof as a challenge here. Don't try to out-idiot the Radian. In this context, I'm just saying that it does most of the math for us. For these next couple tests, since we're going to be pushing voltage and current at the same time, I got to kick my SEL-735 into test mode. I think I recorded a video of how to do that, and if I did, I will put it on screen here. This stops the energy meter from accumulating, and it turns on the test LED on the front of the 735. If you're working with other styles of meter, other brands and manufacturers, you'll need to use the other light sensor. I think it's a little magnetic doodad, or wire up the KYZ output on the meter. All these do is send a light pulse or close a contact back and forth at a very precise time, at a very precise amount of energy repeatedly. So, if you think about those old school analog watt-hour meters, they had a disc, and every time the disc would rotate, it would close a little contact every couple kilowatts, every couple megawatts, whatever it was set to. We're essentially doing the same thing here, except there's no rotating disc. It's just a little blinky infrared LED that we can then plumb back to our Radian RD-21 for the purpose of comparing how much energy that saw versus how much energy the meter we're testing saw. We just need to make sure we get the K, or energy constant, in this case, for this SEL-735, and I think it's default for most of the 735s, K is 1.8 from the watt-hour meter, and then we plug that K value into the Radian, and then they should be essentially expecting the same values. Fortunately, the K value for our SEL-735 here is based on the secondary metering values, which is really convenient because that's exactly what our Radian is expecting, right? We're pushing in the secondary values. I don't tell the Radian what my CT and PT ratios are. It's kind of irrelevant, honestly. I think on some other meters, some other manufacturers, K is scaled, so you'll need to divide your K value by your PT and CT ratios and push that into the Radian scaled down so that they're talking on the same scale. Just make sure that the test quantity on our 735 is set to kWh, kilowatt hours delivered, because that's actually what we're doing in this first test. I'm going to put the video up, and hopefully it's timed halfway with what I'm saying. That would be convenient. You're going to scroll through the menus on the Radian. We're going to run a meter test with a sensor and start the test on the Radian while the relay test set is pushing voltage and current. Bear in mind, our 735 has to be in test mode for that little blinky light on the front to work and to not be accruing energy. Once we hit start on the Radian, it'll actually wait to start the test until the next positive pulse of light, or positive KYZ pulse. And then voila, it's just going to time however many pulses and record the energy that it sees and compare that to how fast or how frequently it gets the pulses of light from our 735. The really cool thing about the Radian is that it doesn't give you a bunch of gobbledygook. It doesn't give you a bunch of stuff that you got to like do math to figure out what your error or your passing values are or anything like that. It actually just displays the percent error between the time that it got the pulses and how much energy it recorded in that period. And it gives you a percentage error, and that's how accurate your meter is. So to me, this proves the meter measured all of the following things more accurately than the published tolerance. Again, if our percent error is in that band. We measured voltage, current, phase angle, time, power factor, and energy, all at the same time, all in a single step. Now in this example with the SEL-735, that has a published spec for accuracy at unity, or 100% power factor, or no phase shift between the voltage and current that we've pushed in. And then it has a slightly looser accuracy spec at 50% power factor, or
60 degrees.
Lag, or I guess lead would also work. In this case, I would recommend doing the energy test twice per phase, once at 100% power factor and again at 50% power factor, because we're testing the claims made for accuracy for that SEL-735 that are published in the book, and we can go back to that and say, hey, it's at least as accurate as the book says it is. Now that's well and above what the NETA ATS calls for, but hey, we do what we can, make the customer get the warm and fuzzies about the equipment out there, and honestly, those two tests don't take any extra time. However, you are going to have customers, and this is super frustrating. You're going to have customers that come up with their own test specs and their own bullshit ways of doing things, and basically you just have to do what they say because they're paying you, and it's... Anyway, if you have a customer come at you with their own testing spec for their revenue meters, just follow it. Again, they're not too hard. The one I'll say that I've had a couple customers ask for specifically is they want to have the revenue tested in all 4 quadrants. Some people don't necessarily know what that means. I'm going to cover what that is with an image, I think. Makes more sense than me trying to explain it. Further, how do you test it? How are you going to test all 4 quadrants? How do we test the energy meter in all 4 quadrants? 4 tests. Well, it's actually 12, right? Because you got to do each of them single phase. It's 4 tests on A phase, 4 tests on B phase, 4 tests on C phase. It's 12 tests total, but it really didn't take that much time. Similar to the way that we did before, we're going to run our first test at 100% power factor with current and voltage 100% in phase. So 0 degrees phase shift between our voltage and current. And we're going to record kilowatt hours delivered. So on the front of the meter, make sure that it's the metering quantity is kWh D or kWh delivered or whatever it is. So second, you're going to change the phase angle. I would change the phase angle of just the current to 180 degrees. Leave the voltage where it's at and change the phase angle of the current to 180 degrees. This is still 100% power factor. It's still perfectly efficient, right? It's just in the wrong direction. So we need to change the metered quantity on our 735 to kilowatt hours received instead of kilowatt hours delivered. And we run the test exactly as we did before. And it should just work. So test number 3, we're going to change our current phase angle to 90 degrees. Now this is a power factor of 0. You could run this test for days in kilowatt hours received or kilowatt hours delivered mode, and it'll never finish because at 0% power factor, you are simply providing or consuming no power. All of your energy is wasted. So we need to change our measured quantity on the Radian and on the 735 to kVAR delivered, and then again run that one on all 3 phases. Lastly, very similar to the previous one. We're going to change our current phase angle to 270 degrees and clock the kVAR received quantity. Test all 3 phases. Go figure. Now, that's a few extra steps. It doesn't take all that much time, but I very rarely have customers ask for that kind of test. But hey, if anybody asks, now you know how to do it. All right, I hope you all learned something today. Sorry I didn't get any sexy product photos for my show and tell for you guys. It is what it is. This video is sponsored by me. I get no revenue from YouTube yet, and honestly, I don't really care. I make a ton of money during my day job. If you're in Colorado or you want to move to Colorado and you're a NETA 2, 3, 4, and you want to come work with me and make a bunch of money and do cool shit and learn things, I'll put the link to my LinkedIn page up somewhere, maybe. Shoot me a message. I'll get you a job. We'll do cool shit together and maybe make some videos sometime. Hit the like button, subscribe for more educational garbage like this, kind of low effort. Stay safe. I'll see you on the next one. Thanks, guys.